videos, we've been talking about an average speed. We're still trying to really build up to our calculus topic of instantaneous speed. We're getting close. We're going to move one more step. We're going to generalize what we've been talking about. Instead of talking about average speed, we're going to change this to a more general concept of an average rate of change. So speed is one example of a rate of change. There are many others that we could talk about. We could talk about this in terms of finance. We could talk about this in terms of, well, we already done distance over time because that's your speed. We could also talk about velocity and acceleration, which we will get to in this course, talking about how to find those values. And we're going to see some other examples, especially when we get to applications of derivatives. But for now, I'm just going to talk in general, an average rate of change of something with respect to something else. Many times the denominator is going to be with respect to time. In most cases it will be, but we're actually going to see some examples later on in the course where it's not with respect to time, it's with respect to something else changing. So here we go. We're talking about average rate of change. So how does this affect our formulas that we've been talking about? So if you look here, in the box here we say the average rate of change of y, or f of x, with respect to x over the interval from x1 to x2. Notice that we don't have t anymore because we're generalizing it. T usually represents time, so here we're using x to represent anything that could be changing. Alright, so how does this change our formula? Well, we don't have t anymore, we now have x. But really not much else changes. Change in y over the change in x. So like I said, x is our new variable because we don't have t anymore, but everything else is just instead of a t, you're going to see x's. Now, over here, remember we're letting h represent a very small change in our x value. So instead of using x1 and x2, we can represent x2 by x1 plus however much we want it to be changing, or need it to be changing, or must have it be changing, depends on your application. So, what is this really telling us though? If I wanted to visualize this formula, what is this? Well, I want you to remember something from maybe past math courses. This delta y, delta x is something that you've probably heard of before. So think about that. Where have you seen this notation? Delta y over delta x. Change in y over change in x. You should recognize this as being m, the slope of a line. Now, in our case, we're working with a function. The function could be any kind of curve. It doesn't have to be a straight line, not at all. The more interesting the function is, the more interesting the discussion of rate of change would be. So, how do we relate our rate of change, or average rate of change, to a line if our function is not a line? Well, I want you to look at this picture down below. We have 2 points here. We have x1 and we have x2. With their corresponding y values, f of x1 and f of x2. Think of the value between x1 and x2, the distance between x1 and x2 as being your h, because that's what h is, it's the change in x. Well, what is delta y over delta x between these 2 points? Well, it's the rate of change of the curve from that one point to the next point, between those 2 particular points. It is that, but it's actually something more than that. Notice how we can connect those 2 points with a straight line. Now this is not our function, this is simply a straight line connecting the 2 dots, 2 points that we're interested in on our function. This straight line has a special name. We call these secant lines. A secant line is simply a straight line connecting any 2 points on our function. Well, how does the average rate of change appear in the graph? Well, we already know the average rate of change is the slope between those 2 points. So the average rate of change, it turns out, is the slope of the secant line. Writing funny. Connecting, what are our points called? Our points P and Q. So that's how you can visualize the average rate of change. So you pick any 2 points on your function, draw a straight line through them. The slope of that line is the slope of the secant line. That is your average rate of change between those 2 points. If I pick any other 2 points on this curve, I would probably end up with a different secant line, which means I would have a different slope, more than likely. And it could be the same slope, but very unusual. All right. Well, now that we've talked about secant lines, and we've related, here you go at the bottom, secant line to the average rate of change, we're going to now take this further. We're going to use secant lines to build up to our calculus topic. This is a topic you're going to see repeated over and over throughout the sections. You're going to be asked to find this type of line many times throughout this course. This is a very important topic. So that topic is tangent lines. So tangent lines are, well, they're used a lot in calculus, to put it mildly. I'm going to try and draw you a picture of how we create tangent lines. So first, let me read the description for you. Tangent lines. For a point P, so let me pick a point P on my curve here. We're going to call this one P. We will define the tangent line at that point P to be the limit. Now, have we really talked about limit? No, but I'm going to kind of guide you towards the concept as we go through these topics. To be the limit, if it exists, of the line going through PQ, from P to Q, as Q approaches P. So let's pick a Q point. Let's pick one over here. Okay. So Q is going to get closer and closer to P. P is fixed. P is not going to move. But Q is going to keep continuing getting closer. So let's call this Q1. And then when we move it, we'll call them Q2 and Q3 and so on as we go towards P. Our method to accomplish this is to consider the value of the slope of each line as Q approaches P. So we need a line. Let's connect the dots here. Let me get my line. So we connect the line, or connect the dots with a straight line. There's our first one. This line is a secant line. It's connecting 2 points on our function, on our curve. So this line, the secant line, has a slope. That slope is the average rate of change. So this is the slope of the secant line. Okay. Now, what we're going to do is we're going to let Q1 move along the curve towards P. So let's pick a new Q. Let's pick this one right here. We're going to call this Q2. Now, we have P and Q2. We're going to draw a new secant line connecting these 2 points. So let's connect P and Q2. Kind of missed. Let me fix that. There we go. Trying to get as good as I can. All right, so we have a new secant line. This secant line has slope M2 because it's the second secant line we're building. It's Q2, so we'll call it M2. Again, this is the average rate of change from P to Q2. We're going to continue this process. We're going to have Q3 right here. Q3 is going to have a new secant line. All right, so this Q3 is going to have a slope 3 for the secant line. As our Q's continue to move around the curve, we're going to continue getting more points as we go around. So here's Q4, Q5, Q6. I can attempt to draw these, but it's going to get very muddled. So what I've done is I've actually provided us a very nice, already printed version of this to help illustrate what's happening in a very clear fashion. So let me go to my next slide here. So here's what we've been talking about. We have our point P, right here, and we have our point Q. These were our initial 2 points. Notice how the arrow is illustrating that our Q is going around the curve towards the P, and these secant lines are also moving in a common direction. The more Q values you do, the closer they get to P, these secant lines are going to approach what we call a tangent line. So let me go back to my picture that I was drawing. So M1, M2, M3, these are all slopes. As we go along the curve, these slopes are going to start approaching a particular slope. That slope is the limit of the slopes. It's what they're approaching. We call it a limit. Once you reach the limit of the slopes, that is when you have achieved your tangent line. So all of these secant lines are approaching this one here, which is a tangent line. and that is what the slope values are approaching. So M1, M2, M3, dot, dot, dot. If we continue that around, those values are going to start changing less and less and less, indicating that we're approaching a value which is your tangent slope. So this is an example of how secant lines are used to create tangent lines by taking the limit of the secant lines. Now we could also do this in the other direction. So if we were to start Q on the other side of P and continue to make Q closer and closer and closer to P, notice the same thing happens. You build secant lines, and the secant lines will approach this one tangent line. If they do not approach a tangent line, then there would not be one in existence for that scenario. We will see that happen in cases, but I'm not going to focus on that in this video. We'll talk about cases where the limit doesn't exist later. So for today, we're going to assume there is a tangent line, and we're going to show you an example of how to find a tangent line without a picture. So find the slope of the tangent line to the parabola y equals x squared at the point negative 2, 4 by analyzing the slopes of secant lines through that point, negative 2, 4. Write an equation for the tangent line to the parabola at this point. All right, what is this asking us to do? Well, we're going to call this point that they're giving us our point P. This is the point that we want to find the tangent line at. So how do we do that? Well, we have to find the slope of the tangent line. But the slope of the tangent line we determined was the limit of the secant. So we take the limit of a secant, or the slope of a secant, and then we watch and see what those are approaching as we move our second point, which they didn't give us, we have to create that. We create a second point, we watch what the slope of the tangent lines, slope of the secant lines do, and we see what our limit will be. So remember, the slope of the secant line is just a fancy name for our average rate of change. And we know that formula. I only have an x1 and x2, that's my P, x1, x2. So not x2, sorry, y1, x1, y1. So what I'm going to do is I'm going to use the formula for average rate of change that involved x1 and an h. So f of x plus h minus f of x all over h. This is going to be the most common formula for you to use when you're talking about rate of change, when you're trying to find a limit. All right, so what does this mean? Well, we have a function. That's our y. Remember, y is just another name for f of x, as long as the function, or as long as the equation is a function. So this is our f of x. Well, the formula says we need f of x plus h. Remember what that means? That means you replace what's in the parentheses with x plus h, which means everywhere else you see an x, you replace that x with an x plus h. So instead of x squared, I'm going to put parentheses squared, and inside I'm going to put what we're replacing the x with, x plus h. So square that out. Remember, parentheses squared simply means parenthesis times itself. So FOIL, x squared, plus, if you combine the two middle terms, you'll end up with x plus h and x plus h, so two of those, and then h squared at the end. So in our formula for the slope of the secant line, we're going to plug in what our information is using the function that we were assigned. So f of x plus h, we work that out on the side. That is our x squared plus 2xh plus h squared. Then our formula says we need a minus sign, minus, we need f of x. F of x is simply x squared. All of this is still over h. Remember, h is h until we're ready to take the limit, until we're ready to let h get as small as possible. All right, so let's simplify here. What can we do to simplify this? This is algebra, just work it out. So the x squareds on top have opposite signs, so those can cancel out, which leaves us with 2xh plus h squared over h, which equals, we can reduce by h, every single term by 1h. So we end up with 2x plus h. There you go. So this is the simplified formula for the slope of a secant line. Now we're interested in the slope at the particular point, P, which is negative 2, 4. So the slope of the secant line here, at this particular point, we plug in our x value. X is -2. So 2x is -2 plus h. So the slope of the secant line here is -4 plus h. So from our point P to our point Q, this is the slope. However, remember, Q is approaching P. It's trying to get closer and closer and closer. As Q gets closer to P, the distance between their x values is going to go to 0. So if h goes to 0, then we have taken Q all the way as close as we can to P. That means we're at the slope of the tangent line now. So the slope of the tangent line is when we let h go to 0, we let h approach 0, we find the slope of the tangent line is -4. We are almost done, but all we have so far is the slope of the tangent line. The question asks us to find the equation of a tangent line. So how do you find the equation of a line? This is something that you should know from previous algebra classes. If you don't, we'll refresh it real quick. To find the equation of a line, you have a choice. Y equals mx plus b, or y minus y1 equals m times x minus x1. The first one is called the slope-intercept form, which requires you to know your y-intercept, or you plug in your point for x and y and solve for your y-intercept. The second one is called the point-slope form. This one is my favorite. I prefer it because you plug everything in and you work it out from there. You can do either one, they both will get you your answer, but I'm going to do the point-slope form. So y minus y1 equals m times x minus x1. To use this formula, you need two things. Your slope, for, in this case, we're doing a tangent line. Remember, our slope was -4. And we need a point. Well, they gave us a point that we want our tangent line at. The point was -2, 4. That's everything you need. So remember, -2, 4, that's going to be your x1 and your y1 in the formula. So plug it in. Y minus y1 is a 4. M is a -4. And x minus x1, careful here, x1 is a -2. Your formula also has a negative. So you end up plugging it in and turning that into a +2. So -x1 but a -2 become +2. Work it out. I'm going to distribute the -4. Make sure you distribute the negative with the 4 to the parentheses. So -4x, -4 times 2 is -8. Almost done. We just bring our 4 around. We get the y by itself. Traditionally, when we write a straight line, we like to leave it in the slope-intercept form. So we combine, we get this one right here. What is this? This is our tangent line to y equals x squared at a particular point on the curve, -2, 4. If you change points on your curve, you will get a different tangent line. So it's very important that you use the right point to find the right line. That's an example of how to find the tangent line from using the average rate of change formula. Make sure you practice, make sure you do your homework. It's very important that you study and practice these concepts so that we can build upon what you already are confident in. All right, good luck.